Hi everyone. I wanted to take some time to help you with your enzyme active site design. So this is the lecture 7 homework, making glutamine from glutamate. And I realized a mistake that I put. I said that it's from your lecture 6 notes, but it's actually, this problem is from your lecture 6 homework. So sorry if it caused any confusion. But yeah, what I want to do is go through this mechanism. We're going to make it into an enzyme active site, which sounds really fancy, but hopefully I can break it down and show you that there's some real simple components that make this very doable. So the first thing that we're going to do is we're going to review the mechanism by itself before we add any enzyme active site type things. And so in this mechanism, we're going to be taking ATP and reacting it with glutamate. So we're going to draw our abbreviated form of ATP, basically only what we need. So I'm going to draw 1-phosphate explicitly, and then the remaining phosphates I'm just going to write as ADP, right? So we have 2 phosphates along with the adenine group there in that little box. Glutamate here can go ahead and attack directly that phosphorus and kick those electrons over. So in this particular case, right down below, I said draw the mechanism with the H and the B first, but you can see from this mechanism there's no protons or bases necessary. So right here we've already checked off one little box in terms of designing our enzyme active site. There's one less thing for us to do. So I'm going to leave this alone and go to the second step, and then on the next page we'll make it into the actual active site. Okay, so you'll notice what we're doing in the second step is we're converting this acyl phosphate into an amide, and we need to do that by having the ammonia attack on that carbonyl. I'm going to pause this to make some space. We have a nucleophilic acyl substitution reaction that's happening, which means we're going to have an intermediate. Notice up above, this was a nucleophilic acyl substitution reaction as well, but because it was on phosphorus, it's okay to be lazy and have no intermediate. So that's what I mean by it's lazy, there's no intermediate, whereas any other NAS reaction is going to need a reaction intermediate. If we start thinking about bonds broken and formed, we note that we have 3 hydrogens on ammonia in the starting material and only 2 in the product. So we know at some point that nitrogen is going to need to lose its proton, so why not do it in the beginning? Let's situate our ammonia group over here. We're going to highlight that one of its hydrogen bonds, be careful how I say that, one of its bonds to hydrogen is highlighted. And we're going to need a base to remove that proton. These 2 electrons are going to kick over to that carbonyl, breaking the nitrogen-hydrogen bond and forming the new nitrogen-carbon bond. These electrons kick up, and this is where our intermediate comes in. We're going to keep everything else that's not involved. I'm going to call all of this stuff an R group. That's okay to do because that's not participating in the reaction. So there we go. There's our R group. That phosphate is still there. This is now negatively charged. If you had it pick up a proton, that's fine too. You just have to remove it in the next step. And then there's our new nitrogen. If we're keeping track well and thinking of where did those electrons all come from, I might even be super picky and show that that is green. I hope you can see that's green, but that's where those electrons came from. So that's our reaction intermediate, and I'm going to put some brackets around it. In order to show this reaction finishing up, we kick these 2 electrons down to form the carbon-oxygen double bond, and then we have inorganic phosphate leave, being careful to stop that arrow on the oxygen, right? So this inorganic phosphate is really this guy here. Okay, it's just another way of writing the anion. Great, so that's the mechanism with B's and H's first. That's my recommendation anytime you're getting ready to draw an enzyme active site. And from there, the next step in terms of drawing enzyme active site is to replace any B's and H's with amino acid residues. In this case, we only have 1 base that's here. And again, you might have used an acid to, over here, you might have used an acid. If you protonated that in the middle, that's fine. I may have done that in the key, I'm not really sure, but I'm trying to keep this kind of as simple as possible. So if I'm going to turn this into a active site, I'm just going to say, all right, instead of this base, let's use aspartate. Let's use an aspartate residue, which is an amino acid side chain, and have that act as a base. And that's sort of like the simplest part to make it more like an enzyme active site. Now, based on the questions I've been getting from students, I think this requires a little bit more explanation before I just do the stuff to make it into an enzyme active site. And by that I mean, let's remind ourselves what an enzyme is. And an enzyme is, in a very cartoony format, it is a long peptide chain, hundreds of amino acids in its primary sequence. So this is all one protein molecule. Now, some enzymes have multiple protein molecules, hemoglobin, for example, but let's just for right here say that this enzyme that we're talking about for these reactions is just one molecule, one string of amino acids, right, that have their own primary sequence. Now, where it has an N-terminus at one end, and I forget where I ended, let's say that I ended over, I don't know, I'll just like make a new end. So it has a clear ending point and a beginning point. Within somewhere, anywhere, somewhere within that, that enzyme, we have a zone that we call the active site. And this is just typically a very small portion of that protein molecule where the magic happens. And by that, I mean, this is where the organic reaction happens. Now, within that enzyme active site, you are going to have several things. You are going to have bases, right? So within this enzyme active site, you may, if you need them, you may have some bases, you may have some acids, you may have some metals, and you are definitely going to have a series of stabilizing factors that are going to help keep your substrate, for example, this guy here, in place, as if you were to take this molecule and put it inside that enzyme active site. Like, how would it actually stay in place? Now, the other thing, just because I didn't write it specifically or explicitly, we definitely do have the peptide molecule itself, and whether it's the peptide backbone or whether it's the side chains of the amino acids that make up the peptide that could be acting as acids or bases. So those are all the little things that are within the enzyme active site. And you can think about the enzyme active site being just another part of the protein. So let's move on down here a little bit and show a little more specifically what the enzyme active site might be. And I'm going to erase all this business here so we just show what matters. So within this enzyme active site, we have sort of like a set of string lights, if you will. So we have let's do our peptide mantra, where we have nitrogen, carbon, carbonyl, nitrogen, carbon, carbonyl, nitrogen, carbon, carbonyl. And so this is one very small portion of that peptide backbone. And then let's say we have some amino acid side chain here. And let's go ahead and say that that side chain, I'm just making this up, is a serine residue. We would call this, so I'm going to be real specific. Remember, what I just said was this here was a serine residue. That means it's a part of the peptide, coming off of the peptide backbone, and it could be helpful maybe in stabilizing your substrate. It may serve other roles that we're just not going to get into here. But this is just one little part of it. And then, there's another side chain here. I'm just going to call that an R group. I definitely put a carbonyl there prematurely, so let's get rid of that. But there's other other side chains happening, and that's all still connected to that enzyme backbone. And the enzyme backbone just continues on, right? So we're showing how we have a very long peptide chain, and it's all, it's not really, I don't want to give you the misconception that it's a circle, but it's a zone. It's a zone where the actual magic is happening. So we already have in our example here our molecules and the reaction is happening. So the only other thing that we need to do is to add our stabilizing factors. These are the things, the forces, factors, the forces that keep these two molecules in place. The two molecules being glutamate, that I already circled in pink, and then ATP, which is written there in green. And because I set up the peptide backbone the way that I did, I can go ahead and draw that there could be some hydrogen bonding, H bond, in between the oxygen of that serine residue and the hydrogen of that NH3 group. I could also have hydrogen bonding in between one of the oxygens of the carboxylate group there and the peptide backbone. So what we have here, hopefully this is not too much highlighting, all of this stuff, right, including the oxygens, these hydrogens, we call all of this stuff the peptide backbone. Okay, so we see our substrate, in this case glutamate, is interacting with the peptide backbone, and it's stuck. It's stuck in that place inside of the enzyme. Now we also need to show how that ATP is bound, and I gave you instructions within the homework to show that it's actually bound to a magnesium ion, and this is just ionic bond formation. It's maybe a little more loose than that because that magnesium can actually hang out with multiple different oxygen atoms, not just the two. And so if you want to think about how that magnesium could be put in place, well, maybe we start thinking about, well, maybe there's an interesting identity of that R group. And maybe we have another carboxylate group, right? So this would here, in this case, if that is our side chain, we would refer to this as an aspartate residue, not a full aspartate molecule. Okay, so this would be an aspartate residue. And this could also be associated with magnesium. So not only is the magnesium being held in place by that aspartate residue, but the ATP is hanging on to the magnesium and holding it in place. So this is one example of making an enzyme active site where there's no acids or bases involved. We're just showing how it's all coordinated to the peptide backbone and other side chains as well. So let's go on, move to the next step in this reaction. And the next step is to take that phosphorylated glutamate, add ammonia, and make it into glutamine. I'm gonna start with just the very first part of that reaction. So I'm gonna erase some things here in a second. Magic. So this is all we care about in terms of designing the enzyme active site. It's what's happening when we start. And we had already taken that base and identified it as an aspartate residue. We can be a little more specific about how that's actually bound for clarification. That's why I'm doing this video, to remind you that this is bound to the peptide backbone. So make sure I do this right. That way, cool, so nitrogen, carbon with a side chain, carbonyl. Thanks for your patience. Okay, so that's all part of the enzyme, and this is just the peptide backbone part. This is an aspartate residue. That's a side chain coming off of that peptide molecule. Carbonyl's there. We have our nitrogen. I'm just going to keep it going. Carbon with a side chain, carbonyl, nitrogen, carbon with a side chain, carbonyl. Okay, so that's going to continue as part of the enzyme, and we can see our peptide backbone. I'll highlight in green like I had before. All this stuff is considered to be the peptide backbone. Everything else that's coming off, those are your amino acid residues. So what we've done is we've identified just a little more specifically where it is. Now, you don't have to do all of this. What I had before in terms of the asp CO2 was fine. I'm just getting more explicit. We do want to show how that ammonia is held on to or is like actually hanging out in the enzyme active site. It's not just floating around. And I happen to situate that carbonyl oxygen of the peptide backbone near one of the hydrogens, so I can show that there is an H bond between the peptide backbone and ammonia. And we can do something similar to try and get an idea of how. All right, so here's the rest of the molecule. That peptide molecule, we can start thinking about how this might be bound. So maybe we have, you know, the carbonyl of the peptide backbone. That's a little bit close. All right, so maybe that's hanging out. Nitrogen, carbon with a side chain, carbonyl, nitrogen, carbon with a side chain, carbonyl, nitrogen. Okay, so this is like more molecule stuff going on. This is more of the enzyme. I'm gonna put my hydrogen there, and I just happen to situate it in such a way that we have these groups coordinated to each other. So this is yet another hydrogen bond between the peptide backbone and the substrate. And we see here, there's another opportunity for a hydrogen bond. Remember, you can only do hydrogen bonding as a donor if you have an NH or an OH bond. You could have an acceptor in a couple different ways. So you could have the acceptor be, as we saw up above, the oxygen, basically any oxygen, could be the oxygen of a carbonyl or an amide, or this could be, you know, accepting a hydrogen bond from a nitrogen, right? And it could be a nitrogen that has its own hydrogen and stuff going on, but those are just some general examples of hydrogen bonding. Now, in the answer key, I didn't put this much detail in. You don't need to put this much detail in. Now, this is very, very nice, and I'm a little bit afraid to erase stuff, but I wanted to be really explicit in terms of what what the key actually means. So here we go. I'm going to erase the stuff that doesn't really matter because we're trying to abbreviate and simplify. Okay, so we don't need to show necessarily all of this or all of that, necessarily all of this. We want to show the stuff that is actually bound. So this is a little bit closer to how it's commonly abbreviated in the literature and in a lot of your homework problems. So we would have, you know, just the aspartate is hanging out there. We would have just this group here, and we might have like little squiggles to designate we understand that there's more to it. This is not a dimethylamine group. This is actually part of the peptide backbone. And then again, that's not just a floating amide, that is part of the peptide backbone. So I think that's enough. I'm pretty sure this video is already longer than I meant to make it. So I really hope this is useful to you in designing your enzyme active sites. I hope this simplified it rather than complicating it. But let me just do a little quick summary. If you're ever design an enzyme active site, all I'm asking you to do is first to draw the mechanism, just regular. If you need any acids and bases, start by using B's for bases and protons for hydrogens. Next, if you used any B's for bases and H's for hydrogen, you're going to replace those, the B's and the H's, with appropriate amino acid residues. We talked about a lot of different examples for amino acid residues or side chains that can act as acids or bases. Your go-to base could be aspartate. Keep using that all the time. Your go-to acid could be a lysine residue. And remember, you want to highlight the NH bond so you can show how it's breaking. So that's going to be your second step. Your third step is going to be adding your stabilizing factors. Stabilizing factors is a very broad term. You want to think about how the substrate, maybe there's two substrates, and any cofactors like ATP, for example, how they're going to stick to the active site rather than floating all over the place. Examples of these would be hydrogen bonding. This could be hydrogen bonding to an amino acid residue that's nearby. It could be to the peptide backbone. And then the other example that we saw, this is kind of specific for ATP, you may have some ionic bonds or associations. So for example, how we had the magnesium hanging out with the negatively charged oxygens on ATP. Right, so that's what I mean by stabilizing factors, is how is that held in place? And last but not least, you do want to show that that magnesium is actually coordinated to the enzyme somehow. Most likely, rather than just saying enzyme, I think the example that I showed before was how there's an aspartic acid residue that has a negative charge. It could be anything with a negative charge that is holding it all in place. So thank you very much for watching. I hope you all have a wonderful day, and I'd love to hear more questions regarding this. Bye.